Try not to shed a tear as our time together comes to an end. We're going to talk about a famous and important real-world problem called the traveling salesman problem. The traveling salesman problem. People have been talking about this for a long time, like since the days of traveling salesmen. And this is all about Hamilton circuits in complete graphs, which I said just a few words about at the end last time. I will refresh your memory. All right, Hamilton circuits, remember, very different from Euler circuits. Hamilton circuits are the ones which meet every vertex without repeating any vertices, but probably miss a lot of the edges. All right, so the traveling salesman problem is, anyway, it's about Hamilton circuits in complete graphs. I will just refresh our memory about complete graphs. Complete graphs are ones in which every vertex is connected to every other vertex by an edge. For example, this is a complete graph. It has 3 vertices, but any 2 vertices have an edge between them. There are no vertices without an edge. So this is a complete graph. Actually, that one is called K3. Each complete graph is typically written with a K, and then the 3 in that one means there are 3 vertices. You can do this with 4 vertices. This is the complete graph with 4 vertices, which we write as K4. K5 looks like this. It has 5 vertices, and they have all possible edges between them. That's why it's called complete, because a complete graph has, like, every edge that could be in the graph is actually in the graph. There are no missing edges between 2 vertices. All right? These are complete graphs. What about Hamilton circuits in a complete graph? That's what I said the traveling salesman problem is all about. Hamilton circuits in complete graphs. So finding a Hamilton circuit, I'm going to draw a big K5 here, and I'll give them names just so that we can talk about them. Would you mind if I don't write the dots? They don't really matter, right? This is a K5 with names for the vertices. Is there a Hamilton circuit in this graph? That is, a circuit which hits every vertex once. Is there a Hamilton circuit? The answer is yes. For example, I could do, in letters, A, B, C, D, E, A. That's a Hamilton circuit. If I were to draw that with my red pen, it would be, I'm going to make a copy of this before I deface it, before I besmirch it. A, B, C, D, E, A would be like this. A, B, B to C, C to D, D to E, E to A. Right? That is a circuit. It is a Hamilton circuit because it visits every vertex once without repeating any vertices. Right? Very, very simple Hamilton circuit. Are there any other Hamilton circuits? Is there another way to visit every vertex without repeating any? I think so. How about something like A, C, B, D, E, A? That would look like A to C, C to B is this one, B to D is that one, D to E, and then E to A. All right? That is also a Hamilton circuit. This looks kind of like a little fishy. Fishy on me. Remember that guy? My kids were into that guy. I don't know if maybe you're too old for that guy. Look it up. A, C, B, D, E, A. That is also a Hamilton circuit in this graph. Are there any other ways you could make a Hamilton circuit? The answer is yes. There are many other ways that you could make a Hamilton circuit. In fact, if you're just looking at the letters here, any permutation, would you mind me using that word? Any permutation of these makes a Hamilton circuit. Like, for example, without even looking at anything, I can just say, how about A, D, B, C, E, A? I just make some kind of rearrangement of the letters Now, in an ordinary graph, you would have to check to make sure, is there actually an edge from A to D? Is there actually an edge from D to B? But in a complete graph, all the edges exist. That's the whole point of complete graphs. And so no matter how you rearrange these letters, really it's just those letters on the inside. If I start and end at A, I'm allowed to shuffle around those other letters in any way, and it will automatically make a Hamilton circuit. All right? So it could be like that. It could be like A, C, B, E, D, A, whatever, right? There are many, many ways that you could rearrange them like this. So any permutation, in this case, if I just decided I'm going to start at A, then you can rearrange all the other ones however you like. So any permutation of the B, C, D, E gives another Hamilton circuit. And how many such things are there? There's a lot. In this particular case, I'm talking about permutations of 4 things. And this, I don't know if you remember, what we talked about this back when we were talking about the Shapley-Shubik. How many ways are there to rearrange 4 things in any other order? There are, in this example, 4 factorial, because there's 4 things here. 1, 2, 3, 4, and you can, it's sort of like you have 4 choices about what you're going to put first, and then there are 3 remaining choices for what to put next, and then 2 more for what to put next. So the total number of choices is 4 times 3 times 2 times 1, which is 4 factorial, which is 24. So there's kind of a lot in this particular example. Many Hamilton circuits. In this example, there's 24 of them. All right, that's Hamilton circuits in a complete graph. What does this have to do with anything useful in the real world? I said the traveling salesman problem, which is about this, Hamilton circuits in a complete graph, is actually very useful in the real world. I would bet that some of you here, maybe all of you, have used, at least you don't do this by hand yourself, but the electronics that you use actually have to deal with this problem all the time. Here's an example. Just a little simple setup here. Let's say that, say I'm visiting, this actually is a true story that's going to happen in a few weeks. Let's say I'm visiting my 3 family members. This I have to do every Christmas because my wife and I and the 2 kids, we have to go to see my family, but also my wife's family. This is like marriage problems. It's not really a problem for us, but this is the kind of thing that all kinds of people do. Check it out. So here I'm going to try to draw a vague picture. Let's say I'll put the star. That's me in Fairfield. This is where we live. I also, at the holiday time, need to visit my mom and dad, who live in the Boston area. We also need to visit my wife's mom and dad, who live this way. That is Gigi and Pops. Those are their grandparent names. I've been married for like 15 years, but I still feel weird calling them mom and dad. I don't know how you all feel about this. And any of you married folks out there? It's weird. They really don't like when I call them by their first names, which is what I would naturally do. They prefer mom and dad, which always seemed weird to me. I call them Gigi and Pops now, which is less weird. All right, and we also gotta go visit Aunt Megan, which is my wife's sister. All right, and she lives in Pennsylvania. All right, and Gigi and Pops live in New Jersey. We live in geographically pretty much the midpoint between the 2 sets of grandparents, which is ideal. All right, and how could we? The question is all about what's the best sort of route that I could take to visit everybody and then end up back at home. And there are many ways that you could do this. Actually, the possible ways sort of involve a complete graph of 4 vertices, right? I could, starting from Fairfield, we could go straight to Aunt Megan's and then to my parents and then to Gigi and Pops and then back home. That's one possibility. That seems kind of like a bad idea to me. What I just described was this. That seems like a lot of back and forth, right? So anyway, the idea here is what's the best route to visit everyone and end up back at home. All right? And by best, I mean usually best in a problem like this means that a route which will minimize the total travel distance, right? That's what I mean by best. You want the shortest travel time. Although, as you know, sometimes the travel distance is different from the travel time, but whatever. You want the least cost route according to whatever you care about, time or distance or money sometimes is the limiting factor. All right, this whole problem is called the traveling salesman problem, and it was first, the name comes from, I mean, this scenario I'm describing is about me trying to visit my family, but the name traveling salesman problem comes from the concept of a traveling salesman who sort of has a big list of houses that he needs to visit to sell his typewriters or whatever, and it's up to the traveling salesman to decide in which order should I visit these 10 addresses that I have on my list. I gotta go see all of those people, but how should I route it so that the total trip has is the most efficient? So this is the traveling salesman problem. All right. How to visit all the vertices. That makes a Hamilton circuit, by the way, visiting all the vertices without repeating anything in the shortest amount of total time. All right. This is super useful actually in the real world. It's not the kind of thing that you and I, ordinary people, use by ourselves, but this has to be done all the time by people who are like delivering packages or something like that. Now the ordinary mailman typically just like drives down every street, and they probably drive the same route every day. But I'm imagining a scenario like the Amazon delivery guy, the Amazon delivery person, the blue trucks, right? What do they do? Like every morning, the Amazon gives them a truck full of packages, and they have to go to, I don't know how many deliveries these people do in a day, but say they have to deliver 150 packages in a day. I have no idea if that's reasonable or not, but they get the truck full of packages, they get all the addresses, and it's just like a random bunch of addresses. It's not the same addresses every day. The Amazon delivery truck, every day you have to decide a new route to deliver my packages. Probably what they care about is you want to do it as fast as possible. All right? So really what they are doing is trying to solve a problem exactly like this, which I've described here, only instead of 4 locations total, you're talking about like hundreds of different addresses that you have to drive these packages to in a sensible order, right? So the Amazon delivery truck, every day you have to decide a new route to deliver my packages the fastest, and I'm just going to say maybe like with hundreds of addresses. So every day, the Amazon guy in the truck has to figure out which order am I going to do this. Now, I've never spoken to one of those people in the trucks, but I assume that the driver of the truck doesn't actually decide what route they're going to drive. I think Amazon figures that out ahead of time. But anyway, this is, I'll just say this is a traveling salesman problem. I'm going to write TSP with something like 200 vertices, something like that. So it's in the complete graph K200, which would be a very, very big graph, right? It has 200 vertices. you can imagine sort of all in a circle, and then every possible edge connecting all of them. All right. Solving this traveling salesman problem efficiently is a very, very big deal for people like Amazon, but not just Amazon. There are many, many other scenarios in which this problem arises as something that you want to be able to solve quickly. All right. So anyway, let's try and do some real specific examples here. I'll tell you, let's just look at my family scenario here, all right? If you want to really solve this problem, which I do, I want to be specific about this, you have to actually know what every different distance is on this graph, all right? So a real traveling salesman problem is on what we call a weighted graph. It's not just a graph, it's a graph where in addition to the vertices and the edges, every edge has what we call a weight, which is a number, which in typically means like the distance from this edge to that edge. So a traveling salesman problem is on a weighted graph. That is, each edge has a weight, and this is a number. So I actually looked this up. These are real numbers that I have for my little, my simple little scenario. I have the 4 possible locations, which I'm just writing as their states, and then I looked these up on the old Google Maps. If I look at the distance from my house to my parents' house, it is 156 miles. The distance, and I'm just going to tell you all of these numbers here. The distance from my house to New Jersey, so across the bottom, is 152. You can see they're almost exactly the same. Across the top, PA to MA is 355. That's a long one. PA to New Jersey on the side here is 114. And then I have 2 across the middle. The New Jersey to Massachusetts is 315. And the PA to Connecticut is 194. All right? So with those numbers in it, this is called a weighted graph. Those numbers are called the weights, and in this problem, the weights represent the distances. All right? And our goal is we want to find the Hamilton circuit with least weight. Right? The Hamilton circuit will visit all of the vertices, and we want the one which has the least weight. That would be the least total distance that you have to drive. All right? So how can we find the Hamilton circuit with the least total weight? Well, there are a few ways that we're going to try and solve this problem, and we're going to talk about a few different strategies. Actually, we're going to talk about 3 in total. We're going to do 1 today and then 2 next time. Actually, I'll tell you sort of 1.5 today. Anyway, so the easiest way, I won't say easiest, I'm going to say the simplest way to do this, simplest way to find the minimal Hamilton circuit is by just writing down all the possible Hamilton circuits and then checking to see which one is the best. So the simplest way is to write all possible Hamilton circuits and then just choose the best one. And we can do that in this example without too much trouble. I'm going to pull down this picture here so I don't have to scroll. I'm going to try to write down all the possible Hamilton circuits. Remember I said before, those Hamilton circuits are just different ways of rearranging the ordering of the vertices. So I'm going to write, would you mind if instead of writing the full 2-letter abbreviations, I'm going to write something like CMNPC. C means Connecticut, and so on, right? CMNNP, all right? Now, that is what I just wrote there. That's one possible way to make a Hamilton circuit here. What are the other ways? I'm making a little chart here. I'm going to try and just write a complete list of all the other ways. And actually, to do this, you don't even need to look at the picture. You can just look at all possible rearrangements. I started by just writing these letters in alphabetical order, just to keep it straight for me. And I'm going to do all possible rearrangements. It could be, there are two ways you can do it with the M first, right? It could be CMNP or CMPN, right? Those are the two ways you could do it with the M first. I mean first after the C. I'm always going to write the C first and last because I start at my house and I finish at my house, which is in Connecticut. But then the other three, they could be in any order. So I could put the M first in two different ways. I could also put the N first in two different ways. So I could go CNMPC or I could go CNPMC. All right? And then there are two more in which I could put the P in the second position. It could be CPMN or CPNMC, like that. These are all the possibilities. When you have 4 vertices total, you should expect 6 different rearrangements. That's because I'm rearranging only the 3 letters in the middle, and 3 factorial is 6. All right, those are all the possible Hamilton circuits starting and ending at Connecticut. All right, and now which of those has the minimal weight? Well, to figure that out, you just have to add up the numbers in there. All right, so if I were to add this up, these numbers are a little annoying. I did them on my calculator ahead of time. What would you get if I add the weight up for this? So you have to look carefully at each little step here. First, I went C to M, which on my picture is 156. So this will be 156 for the first try. Then I did M to N. On the picture, that's 315. Then I did N to P, which is 114. And then finally, I did P to C, which is 194. All right. You look at each of these pairs of vertices. You find them on the picture and add up those weights. And this number you add up, like I said, I did this on my calculator and I got 779. Sorry, I wrote 144. It's 114. Doesn't really matter, but in case you're trying to do these numbers along with me. Anyway, I said 779. All right, that's the total distance for that particular route. And then we just do this for the other ones also. This is slightly boring, but it's not hard, right? You have to, again, add these numbers up. So I go C to M is 156. M to P is 355. P to N, that's down the left side, is 114. And then finally N to C across the bottom is 152. This one I added up and I got 777. A little bit better. All right, not much difference between the two. Okay? And so on. Let's do the next one. CNMPC. I hope you are capable of doing this along with me. It's not hard. C to N is the first one, 152. Then N to M is the big diagonal, 315. M to P, 355. P to C is 194. And this one, when I add those up, I get 1016. So that one is much worse than the other two. All right, and so on. I keep saying and so on. We're really going to do them though. C to N is 152. N to P is 114. I know this is a little boring. Actually, something interesting is going to happen in this one. P to M is 355. And then M to C is 156. This, if you add those up, it equals 777. Now, we have a tie here. This seems fairly unlikely to me. Actually, this is not really a coincidence. Can anybody explain why we got a tie there? 777 both times. Yeah? Yeah, actually, these two things are really the same route, just in reverse, right? If you look at this one is C, M, P, and C, which is this one read backwards, okay? So actually, if you are doing this correctly, you will always get duplicates. Like this one here is the same as that one because they are the same path going in the opposite direction. Which is this one here? Can you say? Is this one? This is going to match one of the ones we already did, I think. C, P, M, and C. If that is the reverse of C, N, M, P, C, which is this one here, right? 1016. So this one, you can save yourself some work. If you notice that those things naturally pair up as reversals of one another, and this one is the reversal of that one. And so actually you don't have to recompute these numbers. This one is also 1016, and this one is also 779. All right, this will save you half of them. You don't have to actually add them all up. You only really have to do about half of them. All right, anyway, what's the best route then? It's that one with the 777. So the best route is, this is real useful information, for me at least, and nobody else. 156, so it's C, M, P, N, C. Or, if you prefer, the opposite direction. C, N, P, M, C. They're the same because it doesn't matter if you go one direction versus the other direction. On the picture, that would be, just so we can see, C to N first and then to P. So on the picture, it's this one, right? C, N, P, M, C. Or the other way around is the best way to do it. All right. Any thoughts about that? This is solving the traveling salesman problem. Actually, there's a name for this procedure that we just did. This procedure is, I would describe this as boring, but it definitely works. It's not really hard to do. You just, it'll take you a few minutes to do it. This is called, the procedure that we just did, this is called the brute force algorithm. Because it works, but it's kind of stupid. You don't have any big idea here. You are just more or less randomly checking every possible option and figuring out which one is the best. All right? No actual big idea behind it. You are just trying to check everything. All right, I got one for you to try. Yeah, question.
A question. In case of homework or quiz where there are two routes, do we put both of them or just one?
I would expect you. I suppose you mean in your big list here.
It's going to be the same route. Doesn't matter which one. But does it matter the direction that we put, or we have to put?
Oh no, I don't care about that. So here in your answer, if you didn't write both of them, that's fine with me. Yeah. Let's try one. I got one with much nicer numbers so that you won't need to use your calculator. So your job here is find the best Hamilton circuit. Best means minimal weight in this graph here. This is kind of annoying to do with only 4 vertices. It's much worse with 5 vertices. With 4 vertices, you get 6 possible circuits. With 5, you get 4 factorial, which is 24. Anyway, here's the numbers. All right, see what you think. You should write down the Hamilton circuits first. There should be 6 total, although 3 are reversals, so you don't really need to consider all 6. and then add up the numbers. I'll give you another minute and then we'll talk about it. All right, let's talk about them. I don't know if you finished yet. That's all right. I wrote down, first of all the hams, all the different Hamilton circuits. I'm just writing starting with A, right? If you decided to start with B, actually get another list of all 6, but they're all kind of the same as the ones that start with A, just shifted over by a position. So you don't really need to consider any other starting points when you're doing the brute force. Anyway, I will notice straight off that some of these are the reverses of the others. For instance, I have A, B, C, D, A. If I read that backwards, it's A, D, C, B, A, which is down here. So that last one I don't really need to consider because it is just the reversal of the first one, and so you don't have to spend your time adding the numbers up for that one. Also, A, B, D, C, A is reversal is here, A, B, D, C, A backwards. So this one also I'm not going to consider. And the 5th one here is also the reversal of the 3rd one. So those 3 I don't really need to consider on their own because they are reversals. This is the same as the first one. This is the same as that one, and that's the same as that one, I think. Yeah. Anyway, the first 3 are the only ones that really matter. And we got to add up the numbers for the first 3. So this one, I go A to B is 3. So this is 3. Plus, next I see B to C, which on the picture is 2. Next, C to D is 2. And finally, D to A is 1. So it's like that. 3 plus 2 plus 2 plus 1 is 8. I hope you got 8 for the weight of the first one. All right, and then we just do this the other 2 times. So A, B, D, C, A looks like A to B is 3. B to D is 4. D to C is 2. C to A is 5. This one I added up, I get 14, I think. I hope that's what you got. And then the 3rd one, A to C is 5, C to B is 2, B to D is 4, D to A is 1. That looks like 12 to me. I hope you got all of those same numbers. Any thoughts about that? Great. So what's my answer then? My answer is the best one is A, B, C, D, A. Or if you prefer the reversal of that, A, D, C, B, A are the best. Exclamation. All right. That's really all there is to it. This is the brute force method for solving the traveling salesman problem. It works. It doesn't require a lot of deep thoughts, although it takes you a while, and it's kind of a pain to do. Things which are simple but take a long time to do are perfectly done by computers, right? That's like really what computers are meant to do, is individually simple tasks just done over and over again really fast. So this brute force, in the real world, nobody does this by hand. It's done on computers. But I would like to point out the brute force method takes a long time. Even for computers, this is actually a big deal in the real world. That is to say, with many vertices. Because, for instance, the guy in the package truck with, say, 200 packages every day, if you actually want to find the best route using the brute force, you have to write down all the permutations. So if we have, say, 200 vertices, this makes, you can decide, I want one to go first and last, but you have to rearrange all the other ones, which would be 199. This makes 199 factorial possible hams to check. This right here is a very, very big number. I mean, like, way too big to actually make all of those checks, even if you're using a computer. This is a number, like, if you try to do this on your calculator, this number has, like, billions of digits. It's way too big. Way too big to check all of these. If you're doing this on a computer, even a super duper supercomputer like that Amazon can run, it's not possible to do this in a realistic time frame. Really, what is a realistic time frame for this problem is like you have to be able to solve this every morning. So at least less than 24 hours is the time that you have to solve this problem every day. And at this scale, this is simply impossible to do, even using like all the computing power of the planet. You would not be able to check all of the possible Hamilton circuits every day. So the moral of the story here is the brute force works in theory, but is not used in practice, but is not practical for many vertices. All right? I am never going to want to visit like 200 of my friends, but the guy in the truck definitely wants to visit 200 different addresses in the best possible way. So this is, for me personally, I don't do this, but actually I use technology that does this all the time. There are similar problems that have to be solved when you are routing internet traffic, which is something that I do all the time. I don't do it myself, but I use instruments which want to do this. All right. Brute force works in theory, but is not practical for many vertices. And something that is this is interesting to me the first time I heard this. No practical method is known. Actually, you can become instantly famous if you can figure out a way to do this efficiently, which does not involve checking all the different cases. This is like one of the great unsolved problems in mathematics. No practical method is known. Actually, as an unsolved problem in mathematics, the mathematicians are trying either to find a practical method or trying to prove logically that it's impossible. But neither of that has been done yet. So no practical method is known, and it's also not known to be impossible. Like a lot of things, you can prove mathematically they are impossible. But this is a problem which is not known either way. If you figure it out, don't tell anybody. Tell me, and I will steal your idea and become a famous mathematician. I am a mathematician, although not terribly famous. I do my own research, and there are people who know me, but you would instantly become super famous if you found a good solution to the traveling salesman problem. Not only is it like just an interesting abstract question, but there are, Amazon would pay you big bucks if you could deliver to them an efficient solution to this problem, which they care about solving every day. All right. So how does the guy in the Amazon truck actually do this if no practical method is known? Instead of actual solutions, so in the real life, IRL, in real life, we use what they call approximate solutions. That is, there are sort of tricks for finding pretty good solutions, which might not be actually the best, because actually finding the best is basically impossible to do even with supercomputers. So we're going to talk next time really about tricks for finding pretty good routes. All right, maybe not the best. That's why these are called approximate solutions. A real solution would be the best route, but that is basically impossible at scale. And so instead, people settle for routes which are pretty good, maybe not the best. And this is actually what the blue trucks are driving on. They are not necessarily driving the best routes because it's not computationally possible to figure them out. But they are driving on pretty good ones, which are computed by much faster algorithms. And we're going to talk about two of those starting next time, I guess. I think that's a good place to end it. All right, I hope you all have a good weekend.